Now I can't do much more than just say it, so you're going to have to maybe take some notes and think about what I'm saying. Setting the determinant of a minus lambda I equal to 0 is our test for the existence of a vector v such that av equals lambda v. Okay, now why is that? Well, yeah, I'll write it out. I'm going to mess things up here, but you've already got it without the mess up, so AV equals lambda v is the same as AV equals lambda times IV, where I is the identity matrix. So that's the same as AV minus lambda IV equals the 0 vector, which is the same as, by linearity properties and so forth, A minus lambda IV equals 0. Okay? So if you've got an eigenvector, the eigenvalue with eigenvalue lambda, this matrix multiplied by V has to give you the 0 vector, which means that this matrix had better not be invertible, because if this matrix is invertible, we can multiply the inverse by both sides. We're going to get V equals the inverse of this matrix times the 0 vector. And what's wrong with that? Well, anything multiplied by the 0 vector is going to give us a 0 vector, and we just get a 0 vector V. And that can't be an eigenvector. An eigenvector has to be non-zero. Okay, so don't really have a lot of good places to write this out. We'll try right here. So A minus lambda I is not invertible. So the determinant of A minus lambda I has to be 0. Because if the determinant wasn't 0, the matrix being square would be invertible. So this equal to 0 is our test for the existence of an eigenvector. And it's a test for the existence of eigenvectors. And it gives you the eigenvalues when you solve the determinant of A minus lambda I equal to 0. Determinant of A minus lambda I is a determinant of this, which is this. Setting that equal to 0, we get eigenvalues, and each eigenvalue gives us an eigenvector. Okay. Now, I'm not going to do a proof of why a symmetric matrix gives us orthogonal eigenvectors, although I could, and hopefully you could. But I am going to prove that this process always gives us a symmetric matrix. Now you can prove the converse of that, that if you've got a symmetric matrix, then you get this, and that does prove that you have orthogonal eigenvectors, but I'm not going to push it that far in a very introductory course. Okay? Now, here, we're going to assume that we have an orthogonal set of eigenvalues. Well, actually, I'm going to go on with this in another video just so I can separate out the explanation over here from what we have here. But you can see how we're setting this up. So I'll pick this up immediately in the next video.